in 2017. He recently received the 2021 AMS Editors Award from the Journal of Physical Oceanography for high-quality reviewing. His research interests include interdisciplinary oceanography, earth system science, and geophysical fluid dynamics. Today, he will speak about exploring the impacts of circulation on biogeochemistry and ecosystems in a warming ocean. So take it away, Dan, the floor is yours.
Okay. Can everyone see my slides and everything in here? Is that good? Okay.
We can hear you. Slide looks good. Go ahead.
Okay. Thank you, Katie. Yeah, so I'm going to talk a little bit about the work I've been doing exploring the impacts of circulation on biogeochemistry and ecosystems in a warming ocean. But first, I wanted to take this opportunity to announce that as of January, I'm going to be moving to the NASA Ames Research Center, Earth Sciences Division in California. And so I wanted to, use this opportunity to tell you a little bit about the work that I've been doing, but also say thanks. It's been a great time being at CGD the last 4 years, and I think it's been really key for my professional development. And so yeah, I just wanted to leave that there. Maybe this talk will stimulate some future collaborations. So with that, I'll just turn to the science. I wanted to start somewhere where I think we all have some common knowledge of. In fact, many of you are probably more familiar with these things than I am, but this is a plot of the global sea surface temperature in an ensemble of Earth system models. This happens to be CMIP-6 results from this recent paper by Kwiatkowski et al. And it's plotted as a delta relative essentially to pre-industrial conditions. On the x-axis, you have time from 1900 to 2100. The black line is the solid black line is historical simulate multi-model mean, and then the various colored solid lines are the multi-model means of various future greenhouse gas emission scenarios, and ranging from high emissions in red down to relatively low emissions in blue. The dotted lines are the analog CMIP-5 experiments. And basically, I'm starting with this basically as a point of contrast to what I'm going to discuss for most of the talk. But what I want to point out here is that if you look at 2100, you see that, say, in the high emission scenario, the increase in SST is, say, 4, perhaps plus or minus 1. The spread is sort of a representative of the range of different model results. And if we look down, say, at the blue relatively low emissions scenario, we get something that is maybe 1.5 degrees C plus or minus 0.5. And so I'd say there's fairly good agreement across models and in a metric like global mean SST in terms of how it will respond to a given level of increase in greenhouse gas emissions. And the fact that we have sort of a range of 4 degrees C across this full range of scenarios indicates that the greatest uncertainty at say 2100 in this metric, global mean SST, is probably what we as humans will do to liberate fossil fuels from the earth and increase the greenhouse gas concentrations, rather than, say, differences or disagreements among models and our understanding of the fundamental physics of the system. Now, let's see. Just to drill down in this a little bit more, I'm showing a map of the century scale epoch differences. So this is the difference now in sea surface temperature between late in the high emission scenario, late in the 21st century minus early in the century, roughly. And I wanted you to note a couple of things. So this is a relatively uniform picture. The changes are roughly 3 to 4 degrees C. So there's a relatively narrow range of changes over most of the ocean. Well, first of all, the whole thing is red, right? So with very few exceptions, almost all of the ocean is increasing by a little bit. There's a relatively narrow range as well, right? So most of the ocean, it's 3 to 4 degrees C. Most of the ocean looks a lot like the global mean, with a few exceptions. And also, finally, there's all these black dots, which are indicating that there's a lot of agreement among models in the regional response. So all over the ocean, the models are agreeing that we're expecting to see, given this scenario, 3 to 4 degrees C warming. And this is, so I'm saying all this, right, to contrast it with many other variables. So it's to highlight this issue that, although some aspects of the global Earth system response to global warming are very well understood, many other aspects are not. And the metric that I'm going to focus on, biological productivity in the marine biosphere, is something that we don't have a good handle on how it's going to respond to global warming, or how it does respond to global warming. And okay, so now this is an exactly analogous plot from the same paper showing the change in percentage terms of net primary productivity of the marine biosphere. It's net primary productivity is the difference essentially between photosynthesis and respiration of marine phytoplankton, the bottom of the marine food chain. So it's sort of a measure of the energy via photosynthesis going into the marine food webs at the very bottom. It's a measure of the carbon. It's a measure of nutrients, if you rescale things. And so it's an important measure both sort of in terms of global carbon cycle dynamics, because it's a measure of how much carbon is entering organic form, and thus it's a measure of the action of the ocean's biological pump, which can affect the air-sea carbon dioxide balance, and thus the atmospheric greenhouse gas concentrations. But it's also relevant for marine ecosystems, right? Because this is the metric of the energy flow into the bottom of the marine food chain. And, on a global basis, but also a local basis, this is a relevant quantity for marine ecosystems. And, there are many other variables that are relevant for marine ecosystems, temperature, pH, and so on, but this is one variable that's important. Okay, so here's the same plot, right? We see the historical multi-model mean in black. We don't see a whole lot of a change. There's some spread between models that's plus or minus a few percent. And then if we look into the future scenarios, we see the high emission scenario red, and the cooler colors, the lower emission scenarios. And I think I want to highlight here, in distinction from SST, right? All of the scenarios are not all that different. They're showing maybe a slight decline of a few percent globally. There's, if we look at the spread associated with the different models, we basically would say that we can't discern sort of the sign of what the response will be in this metric, NPP, global NPP in the marine biosphere. And this is interesting because it actually is a regression from CMIP5, where we thought, following this red dotted line, that we would see a reduction by something like 10% in NPP. So we were fairly confident in that in the previous CMIP5 experiment, and whereas now we're sort of not confident that it will be different from zero. Okay, and so now, remembering the SST picture, here's a picture of the epic scale late 21st century minus early 21st century differences in the spatial pattern of NPP. And again, this is very different from SST. First of all, the global integral is a sum of large positive and negative values. So we have some regions like the mid to high latitude North Atlantic, the Western Equatorial Pacific, where we have large sort of order 50% reductions in NPP in the marine biosphere. Whereas we have other regions like the Arctic and the Southern Ocean where we have large increases. So anytime we're getting, we know anytime we're adding large positive and negative numbers to get a small residual, we expect to have a challenge with our precision. So we expect it to be difficult, the demands and our sort of process understanding that would be required to get, a precise small residual change in, the global integral would be very high in this case, right? But, I also want to point out that there are not a lot of dots on this map. And what that means is we actually have, even though, locally we have these relatively large in magnitude and percentage terms changes, there's disagreement over a lot of the ocean about even what the sign will be locally, even for some of these larger changes. So, this is something, in contrast to, say, the SST response, about which we have very little confidence in, quite a lot of disagreement among models looking at sort of the late century response to, say, the high emission scenario. And before I move on to what I'm working on, I just wanted to compare with CESM, since that's what a lot of us focus on, including me, what I'll show some results from CESM later. So this is a plot of not exactly the same variable, but a similar variable. And I'll just go through what exactly is going on. First of all, I want to point out that this is a measure, so it's a measure of the change in the marine productivity. And it looks basically, there's got qualitatively the same structures. We have a big decline in the subpolar North Atlantic. We have a relatively big decline in the Western Equatorial Pacific. I've shifted so the plot is centered on 0, which highlights sort of my area of interest, which I'll be discussing up here. You see also increases in the Arctic, increases in the Southern Ocean. So this is basically similar pattern in CESM as we see in the multi-model mean in CMIP6. What I'm showing here actually is the NPP associated, the change in NPP associated with nitrate uptake by the marine ecosystem as opposed to all NPP. And the reason I'm showing just this part associated with nitrate uptake is kind of illustrated in the schematic of the oceanic nitrogen cycle. What in the surface ocean, nitrate productivity is mostly limited by nutrients. One major limiting nutrient is nitrate or nitrogen. And so nitrate is high, concentrations are high in the deep ocean where it's dark and photosynthesis is not possible, but relatively low at the surface generally. And, in the surface ocean, once nitrate is made available by, say, the physical circulation, the organic material can take it up, and then they can, when they die, some of this material, the detrital material, can quickly remineralize to ammonium. That ammonium can then be reabsorbed into organic material, and that we can have this sort of recycling of production in the surface ocean, as material dies and is then reassimilated or remineralized back into nutrient and then reassimilated back into organic form. By focusing on nitrate, we can kind of focus on the part of the production that's associated with physical supply of nutrients from deep water, because when the organic material sinks and is exported to the deep ocean, it remineralizes to ammonium, and then it can then convert back to nitrate, which is much greater concentration than ammonium. Okay, and so I'm going to focus on this quote new production throughout the talk, but that's what that is. It's one measure of the marine biosphere. Okay, and so I just wanted to take a step back at the end of the introduction here and just reiterate what the big questions are. What I'm interested in is understanding how will the marine biogeochemistry and ecosystems evolve in a changing climate under global warming, which looks increasingly likely. How does the physical environment influence marine biogeochemistry and ecosystems? So, here, how does the ocean circulation and how do its changes impact marine biogeochemistry as opposed to sort of other variables that might be relevant? Changing temperature, changing pH, and so on. And I guess, there's a lot of ecosystem feedbacks that go on. It's very complicated. So, I guess my angle is sort of what is the role of the physical environment, and how does that trigger biogeochemical and ecological changes? Particularly here, I'm going to be focused on the role of circulation changes. Okay, so most of the talk, basically the rest from here on out, is going to be about these two papers. They are regional studies about the North Atlantic. Basically, just flip back about this big blue dot right here. And the first paper is, sort of half a review. It's half of it is about the observations of nutrient circulation in the North Atlantic, in the Gulf Stream and the implications in the historical, the last few decades, basically. And then the second half of the paper is an analysis of CESM large ensemble, looking at CESM1 large ensemble, looking at the future changes in the RCP 8.5 scenario, and sort of parsing, the role of advective changes in AMOC and changes in deep convection in the North Atlantic as a driver of biogeochemical change. The second paper takes a different approach, and that's the approach I'm going to focus on here. I'm just going to refer you to this first one if you're interested. But the second one applies a very simple model, basically a theory, and uses the theory to try to build understanding of the problem. And I think I just would comment sort of on a philosophical level, there's three reasons that I think it's useful to look at very simple models here. One reason is that unlike, for this problem, unlike say, sort of pure ocean circulation or ocean physics problems, we have biogeochemistry involved. In biogeochemistry, we don't have the same confidence in the fundamental governing equations like the Navier-Stokes equations in the case of the circulation. And so, fundamentally, the biogeochemical dynamics are empirical in the model, and they involve many parameters. And it's very expensive then to explore, how the system behaves in all possible parameter parts of parameter space. In a very simple model, we can cheaply explore, we really can explore all of parameter space, which is sort of a useful thing to do because the models are nonlinear and there's interesting interactions between the various different parameter sets that aren't always so obvious if you do, say, one-dimensional, crosses through parameter space or something like that. So that's one reason. I think a second reason is that, you have more control over, and it's easier to, I think, sort of control over is sort of from a modeler's perspective, but I think that's related to understanding, ease of understanding the phenomena. And I think this, could, things work out, lead to more insight into how the real system works. Finally, I think what's interesting, we also do in this paper, is that you can use a simple model like this to actually understand the behavior of a more complex Earth system model where, you don't have the resources to really explore the parameter space. That can help you identify things like causes of biases and things like that, or at least develop hypotheses that you might explore in a more complex modeling environment like CESM. So I'm not going to talk about all that here, but that's sort of the basic motivation. So basically, and I'm just going to go through now what the model we developed. First, I'll do it qualitatively, then go through just like the basic equation formulation, then discuss the implications. And the basic idea is that we want to merge the dominant biological scale of variability or variability that we observe in the natural system, which is the seasonal cycle in the North Atlantic, with the dominant driver of longer term evolution and change. And so, when we look over the past few decades at the biological system in the North Atlantic, you see this, what's easy to measure is the seasonal cycle, because it's this big event where we can see from space, the whole ocean turns green there in springtime with this big bloom of phytoplankton. And so that's a very dominant pattern. And the interannual variability and longer term change is quite subtle by comparison. And so the idea here was to try to bring together these two perspectives to understand how to be able to model the seasonal dynamics that are dominant and sort of crucial to the system, and then bring together that longer term, the longer term drivers of change. And so I'll go through first the seasonal cycle, then the longer term dynamics, and then bring them together. So phytoplankton, basic premise here is that phytoplankton require light and nutrients, such as nitrate we were discussing earlier, to grow. And as a consequence, if we look at the nitrate distribution in the subpolar North Atlantic, we'll see a profile that looks like this. This is from the World Ocean Atlas Climatology. We see low concentrations at the surface in late summer and higher concentrations at depth. And this is averaged over 45 to 75 north and 70 west to 10 east. What does the seasonal cycle look like then? Well, August is the local minimum of surface nitrate. As fall and winter comes, the solar radiation goes down, mixing in the ocean increases, and nitrate at depth starts to come up to the surface, increasing the concentration, and it reaches a maximum in late winter, and then subsequently declines. And now this plot on the bottom left here is the observed nitrate as a function of depth. That's just the surface part. Depth is on the y-axis, month is on the x-axis. I'm plotting here now, so you can see the decline, low values in August, high values in February at the surface. You can also see that the nitrate distribution is much more homogeneous in the vertical over the top few hundred meters in the wintertime, on average, less homogeneous in the summer. And the more homogeneous time is associated with deeper average surface mixed layers across the region. Okay, and I'll just sort of schematically take you through what happens biologically here. As mixed layer is very deep in March, say, it shoals rapidly as the light and the incoming solar radiation increases. That causes the water column to stratify. It also facilitates photosynthesis. Those two factors together are very advantageous for phytoplankton biomass accumulation, because they only have to accumulate over a very thin layer right here when that mixed layer shoals, and the light has increased, so the photosynthesis is more effective and they've got plenty of nutrients. So what you tend to see is this big bloom of chlorophyll at the surface. Grazers catch up, the nutrients run out, and this tends to decline later in the year. Only later, in the fall, mixing increases again, and then nutrients are returned, but light is low, so you don't get the same response, and the cycle repeats. I would point out a couple of things that are missing from this picture. One is that how does the loop get closed? Biology consumes the nitrate up here. The main way this cycle gets closed from a mass balance perspective in nitrogen is that organic material sinks and is ultimately remineralized back into inorganic form, inorganic nitrogen and nitrate. A lot of this remineralization happens here in the seasonal thermocline, and so it can subsequently be entrained, say the next winter, and produce a sort of closed loop. And that's sort of a fundamentally one-dimensional perspective on the system. Another thing that I'm abstracting here is, it's worth noting, is that there's a fair amount of spatial variability in this simple model. I'm just going to consider this whole region as a single box, but this is plot of mixed layer depth contours in black. We have deep mixing, particularly in the Labrador Sea. Nutrient concentrations in March are higher there. We have deep mixing on the between Iceland and Ireland, and there's higher nutrient concentration there, relatively lower nutrient concentrations and shallower mixing in the central North Atlantic. So keep in mind that there's some simplification going on. So that's the perspective of what's going on seasonally, over the time scale of 1 year. So what happens on longer time scales? Well, I think an important thing before I flip the slide is that some fraction of this material that's sinking down gets to depths below the winter mix layer and is no longer accessible to wintertime mixing. It cannot be supplied back to the surface layer. And so once that occurs, the only way you can keep this system in an equilibrium state is some physical mechanism that resupplies nutrients back to that seasonal thermocline above the depth of the winter mix layer, where it's accessible on an annual basis. And the main mechanism by which that occurs is the overturning circulation, at least in this region. And so just to put some numbers on that, I'm plotting a section, hydrographic section, depth on the y-axis here, latitude on the x-axis. We have nitrate concentration plotted in color. We have very high concentrations in the main thermocline, say 500 to 1,000 meters depth in the tropics and subtropics. Lower concentrations in the low concentrations, obviously, virtually everywhere at the surface, but lower concentrations at depth in the high latitudes. The isopycnal contours, like isotopes in the atmosphere, are plotted in white. The flow tends to follow these isopycnal surfaces. The northward limb of the zonally averaged vernal overturning circulation, mostly flows, sort of above 27.5 to 27.7. So it's mostly in this region. Flows northward. It carries about 0.35 megamole per second of nitrate, into this subpolar North Atlantic, and it flows upwards along these slanted isopycnals towards the surface in this region here. And this is a key reason why over a long time we can sustain high productivity in this region. And then what happens is some fraction, North Atlantic deep water is formed, and some fraction of this nitrate is just subducted downwards and flows south at lower concentration. And there's also sinking organic material, some of which is lost from that seasonal thermocline, and no longer able, needs to be replenished by this northward limb. And just to put these numbers in perspective, this 0.35 megamole per second, what does that really mean? It doesn't even really mean a lot to me, but I think this helps. So if you think about, I looked up what the global anthropogenic end fixation from fertilizer production due to humanity is. It's about 0.475 megamole per second on average. That was 2013, so maybe it's increased since then. I'm not really sure what the trends are, but that just puts it in perspective, right? So the Gulf Stream and the overturning circulation are transporting in the North Atlantic more nitrate poleward just in this region, or not more, but a similar magnitude of nitrate poleward into the subpolar North Atlantic is all anthropogenic fertilizer production globally. And so, if we can imagine if there's going to be substantial perturbations in the overturning circulation, say 20%, 40%, in the context of unabated emissions in the 21st century, then this sort of perturbation to the nitrogen cycle of the North Atlantic will be far larger than sort of any expected anthropogenic perturbation in that region, relatively small region. And just also to sort of take a different tack on putting this in context, if you take, just to put a time scale on how this sort of 0.35 megamole per second operates, if you integrate the nitrate above 1 kilometer depth in the North Atlantic, it's about 200 gigamoles. If you divide that by, say, 0.3 megamole per second, you get about 20 years. The point here is not to get these numbers precise. The point is to say that the flushing timescale for the upper ocean nitrate reservoir is about, associated with the overturning circulation, is about 10 years. So it's pretty quick. And, you might think of other processes that might be relevant for supplying the upper ocean nitrate in this region, things like turbulent mixing associated with internal wave breaking, or, pick your other favorite process. That process is expected to have a time scale, a flushing time scale for the upper ocean nitrate reservoir of order centuries. So, much longer. And so when we're talking about global change on time scales of several decades to, a century, this changes, substantial changes in this overturning circulation can be very important. Okay, so that's the sort of qualitative picture. We have this sort of seasonal cycle modulated by this overturning circulation. And then, there's some interannual variability, which I'm ignoring at this stage, which, there will be an interesting interplay between these two processes at sort of intermediate timescales, where sort of variations in the seasonal dynamics and mixing, and then variations in overturning might have competing roles in terms of how they're driving biogeochemical change. But I'm going to focus on the sort of century scale response of this. And just to put some equations on it before we get there, it's actually relatively simple what goes on. You can explain the seasonal dynamics during fall and winter in terms of entrainment. the surface nutrient concentration increases as higher nutrient concentrations from the seasonal thermocline and our quote deep box, are entrained with an entrainment velocity that's equal to the rate of change of the surface mixed layer depth. That's the surface layer ds. This is the surface nitrate concentration. So this can reasonably well explain why the concentration of nitrate in the surface increases in wintertime. In springtime, the surface concentration of nitrate decreases. That can be explained reasonably well in terms of the increase in the available incoming solar radiation, which facilitates photosynthesis, productivity, biological productivity, which is limited by both nitrogen concentration. So we have this like non-dimensional limitation of productivity by nitrogen and a non-dimensional limitation by the amount of light that comes in. And you can tune this, you can right away see in this very simple model, we already have a bunch of parameters here, but you can very, very adequately explain the, describe the dynamics of the nitrate drawdown at the surface in springtime with a simple expression like this. And this is this 1D process. And it turns out that you can, in the interannual mean state, explain the long-term balance that arises from the overturning circulation with just this expression here. So you have to take the productivity on one side and you multiply that by the fraction of the nitrate uptake, new production. So it's a nitrate uptake in photosynthesis that's prod, and then you multiply that by the fraction of productivity that penetrates below the seasonal thermocline, below the winter mixed layer depth, and is thus lost from the upper ocean system on an annual basis. And we can actually write that fraction here as this exponential of minus the winter mixed layer depth divided by delta. And so this is a key parameter here, which will change in global warming. It's the winter mixed layer depth divided by the E-folding depth scale delta, over which sinking and otherwise downward transported particles and organic material of all types is remineralized back to nitrate. And on the right-hand side, we essentially have this quote restoring by the circulation, which we express in terms of the maximum magnitude of the overturning stream function in density coordinates at 45 north divided by the area. So that's a vertical velocity scale times the difference. This is a nitrate deficit in the subpolar North Atlantic seasonal thermocline relative to the subtropics, right? I'll just flip back here, right? So it's the deficit in nitrate here relative to here, essentially. Yeah, and so, okay, so that's the basic concept. This explains quite well, we'll see the longer term equilibrium. And this allows us, so we have a model where we couple these two processes and they're solved for dynamically in a transient fashion. We go through an optimization procedure in the paper to obtain a good fit, parameters that fit well, produce a good fit to the observations of the nitrate climatology. This is the observational seasonal cycle of surface nitrate. The red is the modeled. It's only a 2-box model, but we have a surface layer, and we can see that we can match the time mean surface nitrate concentration and get a reasonable good concentration in the seasonal thermocline. For reference, I've put CESM on here. So CESM also does very well at simulating the surface nitrate in the subpolar North Atlantic, but it has a bias in the seasonal thermocline. It has significantly too high a nitrate concentration in the seasonal thermocline. Okay, so this gets us to the question that motivated the whole thing. How does the subarctic Atlantic Ocean biological productivity respond to high emissions in the 21st century scenario? So what all is going on here now, and why do we need all these pieces? Okay, so this is sort of a schematic showing what's going to happen, and then it sort of highlights the questions that we will have. So we have production in the euphotic layer, in this summer mixed layer region up here. There's export of that material downwards. Some of it is remineralized back to nitrate in the seasonal thermocline. Some of it is lost below the winter mixed layer depth dW here. And into the main thermocline, we have this purple arrows are highlighting the flushing of the upper seasonal thermocline by the overturning circulation. So now time and global warming is on the x-axis. What happens is that the surface layer gets warmer, fresher, and less dense. And the mixed layer depth shallows, and the overturning circulation, this flushing, slows. So this has a couple of consequences. One is that a greater fraction of sinking material will be lost from the surface system. That's a negative tendency on, or negative pressure on productivity, because we're losing more of the nutrient supply in the upper ocean. We're also just kind of permanently subducting, some of the material that's here. There's a subduction process. So in a long term, we're just leaving, remnant nutrients down here behind as this mixed layer shoals. And, then there's the reduction in supply coming in via advection. And that's also sort of a downward pressure. And so how do all these pieces come together? How, what is really driving the reduction in productivity? Is it these shoaling mixed layers, or, is it the slowing circulation? Is it this, how does that work out? And I would just say, I think the dominant paradigm at present, and I'm not sure that I can refute it per se, is that, although I'm arguing against it, is that the reason that you see that big blue, decline in productivity in the subpolar North Atlantic and the warming scenarios, because we have a lot of much shallower mixed layers there, and that the consequence of the shallower mixed layers is that we vertically decouple the high nutrients at depth from the productivity at the surface. And so just like the seasonal cycle, if we just imagine a reduced seasonal cycle, all of a sudden we have less productivity. And I'm arguing here that's really not at all what's going on. It's this sort of interplay between changing in the fraction of material that's exported, which is influenced by the mixed layer depth, and changes in the overturning circulation. Okay, so in the model, we actually couple, we actually have a dynamic physical circulation. What we specify is only the surface buoyancy evolution. So we actually couple the mixed layer depth dynamically to the overturning circulation, as well as the biogeochemistry. And so the physical model is described as follows. We have low latitude buoyancy, which is simply an exponential function of as a function of the surface buoyancy, and this depth scale H, which we can fit to present day observations. We have a high latitude buoyancy Bn, which is lower than, which is lower than the low latitude southern buoyancy Bs, and we have a depth scale of the overturning circulation, AMOC, DMOC. So DMOC is this depth scale over, of the overturning circulation, and that is given by this depth scale H, which is fixed, times log of the surface buoyancy in the south and the surface buoyancy in the north. And then using continuity arguments and thermal wind arguments, we write the stream function. This is depth dependent as a function of the difference between the high latitude and low latitude buoyancies. And then we couple the mixed layer depth to the depth scale of the overturning circulation via a constant factor R. And actually what we're going to use as our metric for the mixed layer depth is the mean mixed layer depth of the entire region. And depending on your choice of metric, what your statistic is, mean, maximum, whatever, you're going to get a different value of R. So we're choosing the mean because we think the mean is most relevant to the biogeochemistry. But if you chose a value like maximum of D winter, you might expect an R closer to 1, because that's sort of consistent with the physics of the deep water formation, the very deep mixed layers, and that being subducted to the south on the overturning circulation. But this is how we do this coupling, and we assume this R value does not change. So now I'm just plotting here the winter mixed layer depth as a function of the overturning circulation at 45 north in density space and CSM large ensemble, the high emissions RCP 8.5 scenario. The curve here shows that indeed these two are very highly correlated. through that scenario, ranging from a value of about 300 meters mean mixed layer depth in the subpolar North Atlantic, overturning of about 19 spherodrips, down to something like 150 mixed layer depth and 8.5, 9 spherodrips overturning. And now, so we can use this, that's just for reference. Here's our theoretical model that just is based on these simple expressions. It has a different time evolution of surface buoyancy. We just specified the surface buoyancy to be a linear increase in time. So it's not so much the spacing between these dots that matters, which are every 5 years. It's the trajectory that they follow through the space. And indeed, we find that this simple formulation, and this is an approximate solution to this governing equation over here, shows the overturning stream function as a function of the difference between the buoyancies and the low latitudes and high latitudes at the surface. That trajectory is very similar to CESM and shows how the mixed layer depth and overturning evolve through time. Now, the colors on these dots are annual new production in the marine biosphere in the subpolar North Atlantic. And we indeed see also that these colors are very highly correlated with both the mixed layer depth and the overturning stream function. So that sort of presents a problem with CESM. We can't just sort of do a correlation analysis and say, oh, indeed, the mixed layer depth is driving the decline in productivity, or indeed the overturning is driving the decline in productivity. They're both highly correlated. So which is it, I guess, is the question. And to get at that, because now we have this simple theoretical model, we can just run the transient scenario, but break the physical coupling between the overturning and mixing. And so that's what we did first. We said, okay, let's run the same transient scenario, but just break the coupling between overturning and mixing, and force, say, the mixing to remain at 2020 conditions. And so that's this top trajectory here. The mixed layer remains at 310 meters or so, but the overturning declines, and we see this reduction from about 0.8 to 0.5. And then if we hold the overturning fixed and allow mixing to decline, we see that the biological productivity declines by about 0.1. And it turns out that they're about additive, so that the overall 50% reduction is a combination of, something like 0.3 and 0.1 here. So, but that need not be the case. And in addition, we can go a step further and we can say, we have this relatively simple model. To what degree are the transient dynamics consistent with, well, to what degree, I guess, in general, are the transient dynamics important? And to what degree can we sort of interpret every step along this pathway in terms of this equilibrium dynamics? And it turns out that, the fact that the colors inside the circles are very similar to the colors in the background is showing that the equilibrium dynamics of the theoretical model are very similar to the transient dynamics. So transience in this sort of high emission scenario is not very important by this metric. The equilibrium, the system is nearly in equilibrium all the time because the sort of evolution is slow enough. So the background color in general and the contours shown here are showing the equilibrium value of biological productivity in the subpolar North Atlantic for all these different combinations of mixed layer depth and overturning circulation, with sort of our flexibility to break their physical coupling with this diagonal being the sort of physically realistic coupled form. But I think it's useful to actually look at the different values here, because although we think that there's something really fundamental about the physical coupling of going along this trajectory here, we're not certain exactly how this winter mixed layer depth and the overturning circulation relate in the real ocean. We think there's something fundamental about this relationship that says we're going to do something like this trajectory, but what exactly is the relationship? Well, are we going to go sort of diagonally like that? Are we going to do what CSM does? That I think, is sort of the reason why it's useful to sort of understand this whole parameter space, because the real trajectory may not be exactly what this model produces or CSM, but even if it's qualitatively similar. Okay, I did say that, we were marrying this sort of seasonal perspective and long-term equilibrium, and all this discussion here didn't have anything seasonal in it. So I did want to conclude with a seasonal plot. This is showing the seasonal dynamics in these different scenarios. This is highlighting, the fact that really this is sort of seasonality as a dominant picture here, or a dominant factor here in the dynamics. We have very high productivity in the springtime in the present day scenario, and then declines, smallest decline for just the decline in vertical mixing, bigger decline for reduced overturning, and the greatest decline yet for the sort of physically realistic combination of the two. And we also see that they contribute differently at different times of the year, even though they're approximately additive. This is a nonlinear model. There's no real reason why they should be additive, but it turns out that the effects are approximately additive. And the overturning sort of has the greatest impact late in the growing season. So it's sort of tending to shorten the growing season. And all this is sort of sending us, I think, this is just very, very, very preliminary, right? And we did this super theoretical model, but it highlights sort of how tricky it is to get at what's really going on in a GCM because of this fundamental physical coupling between mixing and overturning. How do we understand what the causes are? We'd have to break that coupling in a GCM, which is possible but tricky. So I think this is suggesting that we should look a little bit more into understanding this. The indication is that remote changes in the Atlantic basin scale circulation are more important than local increases in stratification and reductions in vertical mixing, and increasing fractional losses of new production from the seasonal thermocline in the North Atlantic. And I guess, one reason why you might care is that, a lot of say users of what we do as Earth system modelers, global Earth system modelers, might want to downscale our inputs. And I think it's crucial to understand in this region of the North Atlantic, downscaling is not going to be a very effective solution because it's the result, the result in terms of the biogeochemistry is crucially dependent on the basin scale and global dynamics. In an interesting twist, right, the mixed layer dynamics in the subpolar North Atlantic feed back and exert a strong control on the basin scale circulation as well. So there's a sort of, and then that mixed layer dynamics might indeed be sensitive to small scale processes going on locally in the North Atlantic. So there's this, region where we have interesting interplay between very small scale and large scale dynamics that sort of make it, I think justify kind of the type of work we do here. And so before concluding, a couple things that are ongoing, maybe points of future connection. I remain broadly interested in how the oceans, ecosystems, and society respond to climate variability and change. I think this is a kind of cool figure from the top is just a map of chlorophyll from satellite climatology, but down below is kind of cool. This is a fishing effort, a log scale of fishing effort. So thinking about actionable consequences of what we're talking about earlier. Some of the areas of highest fishing effort occur exactly in the bullseye of where the AMOC might impact biogeochemistry. So that I think is an interesting thing to think about. I just wanted to also say, a big source of uncertainty in these projections for NPP or like global marine biosphere dynamics is the dynamics of particle remineralization, how the particles get down to depth and where they remineralize, and how that occurs in different elements. And I've been looking a little bit at some experiments assessing the role of this dynamics in how it impacts climate change projections. And it turns out that I think this parameter can change the sign. So this may be an important source of the divergence in the model projections. So I'm showing here some CESM large ensemble branches that I did with perturbed remineralization dynamics. And we can see that we can take from sort of a 10 to 20% reduction or a 10% reduction in the control sort of CSM LE case to sort of a negligible reduction just by perturbing in, I think, a realistic way how the remineralization dynamics works. But an important side point here is that the least place in the ocean that is least sensitive to this dynamics is in fact the subpolar North Atlantic. So there's sort of the rest of the ocean where, particularly like the equatorial Pacific, where it's highly sensitive to the dynamics of particle remineralization and export, versus the subpolar North Atlantic, which is really controlled by this physical circulation. I'm also really interested in, small scale processes scaling up, how, some of you are familiar with work that I do with large eddy simulation and turbulence, and linking that to biogeochemistry and ecosystems. I mean, maybe that's something to think about in the future. I think that is relevant to the story I talked about earlier, but it's a bridge to get that linked in. And I just wanted to highlight something here. New 10 PI collaborative project under the Growing Convergence Research NSF thing, which is newly funded and I'm nominally participating in, but my new role will complicate. So hopefully we can collaborate on this somehow. And this is the convergent impact of marine viruses, minerals, and microscale physics on phytoplankton carbon sequestration. It's all about exactly what I was just talking about, how particles get downward in the water column and where they remineralize. My role is sort of computational modeling particle dynamics and ecological dynamics. And I think there's some interesting opportunities. We have a very simple parameterization of how this particle remineralization occurs in CESM. This is a great community of people that I think know a lot of things that potentially could help us make that more realistic. Just wanted to highlight a couple things from collaborators, Matt and Frank and University of Hawaii, some work to look for. They're looking at simple biogeochemical models to try to elucidate the process dynamics globally and in the North Atlantic in particular. And I'm going to skip this and just say thanks. Thanks for giving me the opportunity to work with you guys for 4 years. It's been a lot of fun. I'm looking forward to continuing to collaborate over as time goes on from a new location.
Thanks very much, Dan, and congrats on your new position. That sounds exciting. So if you have questions for Dan, you can type them in the chat box and I can read them aloud, or you can use the raise your hand feature, which is in the Zoom participants window. And I do see we already have a question in the chat from Robert. How sensitive is your annual NPP result to the KN, the half saturation constant for phytoplankton growth? The reason I ask is because the lowest N values in surface waters in the subpolar North Atlantic shown in one of your earlier graphs, I think are above the KN for phytoplankton, which I think are closer to 0.5 micromolar. So the phytoplankton are never N limited.
That's a good question. So I think, so the KN value that we end up using in the optimal model is 3, which is a relatively large value. I agree exactly with the comment about that being a large value. And I guess I think in this context of, so the short answer is they're not very sensitive. I should just say that right up front. Under the assumption that we have to use this model and we have to match observations of present day conditions reasonably well. So we can choose a large range of KN values to fit observational nitrate distributions at the surface reasonably well. But if we change our KN, we have to change our uptake rate. Let me see if I can flip back to the equation. Here's the productivity. So here's this mu m, which is a constant maximum uptake rate, and we have this Kn down here, which is a half saturation for nitrate. In the summertime, late summertime, phytoplankton are probably not nitrogen limited in the North Atlantic. They're probably iron limited, if anything, I would say, based on the literature I'm familiar with. But I don't think actually this is a critical aspect here, because perhaps, well, first of all, the nitrate concentrations are relatively low. They're less than 1, which isn't going to change the mass balance dynamics all that much that we're looking at. And I think, we could have changed Kn without any consequence on the results if we changed mu m in an appropriate compensating way. And it turns out that when we use the observational constraints of surface nitrate and vary both of those parameters in a way that fits observations, the projections of future change are virtually insensitive to the value of Kn, as long as we change μm in such a way that we match present day observations. So hopefully that answers the question. The observational constraint plus this sort of model assumption means the results are sort of, future projections are insensitive to the value of Kn.
Okay, I see a question from Bill Large. Go ahead.
Yeah, thanks, Dan. Yes, your simple model is certainly not simple. And thanks for showing some of the things you can do with it to try and understand what even the more complicated models are doing. But a question I had was, early on in the development, you equated the entrainment velocity to the rate of change of mixed layer depth. And that's true only if the vertical velocity is 0, and yet you're talking about overturning, which is vertical velocity. So what are you meaning by entrainment here? Or you're not making the assumption W is 0, or what are you doing to get that?
Okay, I don't have the equation. So this is actually not.
You said entrainment velocity equals
this
total derivative of mixed layer depth over time.
Yeah, you're looking at this formula right here, right? Can you still see my screen?
Well, yeah, but my participant thing's in the middle. Just a minute. Yeah, that's it.
Yeah.
So are you assuming W is small or?
No. Yes. So I'm not, the model actually, exactly what you're talking about is what actually happens in the model. The model treats entrainment the correct way, which is not this. This is an approximation.
Okay, thank you.
Hence the approximation here. So I should just add that the approximation in fall, this approximation turns out to be correct. And the reason is that the overturning, the vertical velocity associated with overturning is quite small compared to the seasonal, just the autumn time descent of the mixed layer. So actually the entrainment velocity is dominated by this approximation at this time. But we do it properly in the full thing. And the paper shows when in the fall this dynamics is dominant, but at some points in the year, the dynamics are more subtle.
Yeah, and of course entrainment is sort of positive definite, so it can't do shoaling. So.
Yes, that doesn't impact the budget.
Okay, so I understand that. It's just that little squiggle is
that squiggle
not even such a good squiggle. Okay, thank you.
Okay, question from Hu Kim in the chat. Nice talk. Appears that the maximum NPP change takes place further east than the temperature change associated with AMOC decline in CESM. Is it related to the NPP mean state?
Okay, I want to go back to the figure so I can follow the question again.
Sure.
Okay. How do I see the chat? Can't even.
Yeah, I can read it. I can read it again for you if you can.
Yeah, can you read it again? Sorry. Thanks.
Yeah, so it's asking about the maximum NPP change looking like it's further east than the temperature change associated with the AMOC decline in CESM. So is it related to the NPP mean state?
Yeah, I'm not sure what the answer to this is. Yeah, I'm not sure who. That's an interesting question. So I would just I'm not sure what the answer is. I think I'd just step back to say that understanding the spatial variability of what's going on here is an objective for future work. Understanding, why this looks the way it does. I could speculate, but I don't know the answer to that at this point. I think that's a good question to think about in the future.
And who I see that you unmuted yourself. Did you want to add any clarification?
No. Yeah. I think that's enough for now. We can talk later.
Okay. Question from Andrew Thompson. Go ahead.
Turn my camera here. Hey, Dan, nice talk. I am intrigued by your link between changes in mixed layer depth and the overturning circulation.
Mm-hmm.
I would have thought that those density classes that sort of feel the effects of a change in mixed layer depth and not necessarily those ones that are connected to the high latitudes. So changes in mixed layer depth is sort of happening above the thermocline. And what I think about the AMOC is those like intermediate waters and deeper that participate in the overturning. And so in terms of a water mass transformation and thinking about water mass transformation controls on the overturning, I'm a little surprised that you can mechanistically relate a change in mixed layer depth to a change in the strength of the overturning. Although I agree they might be correlated, especially in a warming climate where you get shallower mixed layers and a reduced strength of the overturning.
Let me see if I'm not sure I fully understand your question. Is part of your point that, say, I mean, maybe I could just stop here on this plot, that you sort of expect the change in mixed layer depth only to be relevant to overturning where mixed layers are, say, maximum, like, and where deep water is actually formed, like North Atlantic deep water is actually formed? Is that sort of your point? Am I getting that?
So if I think about the overturning plotted in density space,
Yes.
right, then I think about, you know, outside of the high latitude North Atlantic, most of the overturning stream function is aligned with density surfaces.
Correct.
Right, and most of the transformation happens at the high latitude. So if changes in mixed layer depth are affecting density classes that are shallower than where you have that most of the AMOC, then I'm a little bit unsure how that participates in a change in the strength of the overturning. But maybe they penetrate into the depth of the AMOC or into those density classes that participate in AMOC.
Yeah, I'm not so okay. So I think I understand your question. It's not clear to me either, I think, is the short answer. It's not clear to me. Say, okay, so let's just take for an example, right? Like, I think, you know, say mixed layer depth over here off the coast of Ireland, say, for example, in present day, the March outcropping density there and climatologically, say 27.2 potential density anomaly. This is not, right, this is not North Atlantic deep water. This is some shallower density class that we don't think of as being crucial to sort of the water mass transformation for the formation of North Atlantic deep water, which would occur at denser, you know, denser than 27.5, say. And so we wouldn't necessarily, I agree with you that we wouldn't necessarily, it's not trivial to say that we expect that changes in mixed layer depth in this region over here would direct, and changes in density of the mixed layer, right, at 27.2 there, would directly affect the overturning circulation. I think there's an assumption that this, you know, which is sort of here, that somehow the mixed layer depth system, you know, the whole system behaves in some, you know, consistent fashion, that, you know, as the density increases and mixed layers shoal, that, you know, sort of the entire subpolar North Atlantic behaves in some consistent fashion in terms of the mixed layer shoaling and the overturning depth shoaling, even if the change in mixed layer depth, say, in the particular region that I highlighted, is not directly, or maybe it is directly, but I don't know how, like you're saying, I agree with you, I don't know how exactly that coupling dynamically would work. Maybe there actually is some coupling, but to actually figure that out would be, you know, I think this goes to like kind of whose question as well. To actually figure out what's going on here, why, say, some relationship like this occurs, would be future work. We're just sort of saying, oh, interesting that this, we've speculated this and we can show that it holds, you know, if it holds at a given time, it tends to hold throughout the simulation in CSM. And, you know, it seems to be a useful, I don't know, thought exercise to understand it. Yeah, interesting, would be interesting future work. I don't understand why. Yeah, hopefully that answers the question.
Yeah, no, that's helpful. I think your message that the remote controls on the overturning are important here is a good one. So yeah, that's great. Thanks.
All right, thanks, Dan. We're a couple minutes past the hour, so a couple of quick announcements before we close. So as I mentioned, this is the last seminar for 2020, but please join us on Tuesday, January 5th, 2021, where we'll have Paulette Blanchard from the University of Kansas